Get ready for populations.
What's up, Orango Army?
All right. So before we talk about like everything to do with population, we're going to take it a step back and talk about the two groups species can kind of be broken up into. And it's R strategist or K strategist, or you might have heard R species or K species. There's another word I've hit a blank, but you probably saw this word in bio just to remember. But the R will help you remember something because R stands for what? Let's try to reveal any of these. I guess I'll pause. So how fast they reproduce or reach the age to reproduce versus slow. So our reproductive years start like 12 to 15, right? And then you have like dogs that can reproduce at 1 year old. What else? Good. R strategist, little care. K will care for their young. What else? They're usually small and weak. K are large and strong. And obviously there's a middle, right, ground. You've got the ones that are on the extreme spectrum, which we would be definitely over here. What else?
Any offspring.
Good. R have a lot of offspring, like a dog or you know, any animal can have 6 and 7. We have 1, right? And then in terms of lifespan, short for R, long for K. So we're going to review what's the definition of population. All members of same species. Where? In the same area at the same time. Okay, so any group of the same species live, like we make up the population of this class. If I brought in another organism like a fish or our little shrimp, us and the shrimp make up a what? Community. Us and the shrimp breathing or drinking water make up a ecosystem. Good job. So when we calculate the total number of organisms in a given area, we're calculating the population what? Total number in a given area. Make up the what? No, this would be density. Total number of organisms per unit area, right? So this would just be? Size. Good job. And this graph is not perfect because obviously if you look at this dark here, this is representing something very off. Maybe it means no population. I'm not sure because I looked up the numbers. But if we look at like Texas is highly populated if you know, search how much people live in Texas, but they're so spread out because it's such a large state and they own so much land, they're not densely populated. And that makes a big difference because you can have a lot of people, but when you have a dense population, a lot of other things can happen. And those are the things we're going to talk about at the end. So first, a lot of like terms, a lot of calculating, and then reasons. All right, so organisms can be dispersed in a population, and this really, a lot of these notes will reference human population, not so much this. This is the way they're arranged in the population. You could be uniform, and these are penguins. I know it's hard to see, but you know how they kind of line up, right? And then you've got random, which in this case are representing the flowers, and then you've got clumped. Which of these three do you think is most common in populations of organisms?
Random.
Yes. Let's think why. So random makes sense because you think, oh, they're just going to be anywhere. But why would they be clumped?
For protection.
For protection. Good job. What else? Awesome. They're looking for resources, and you think of these, now that you've studied the savannah, what are they searching for? Grass and water. We know that there's watering holes, right? What else you think makes them be clumped? Good. Group work. Look what's happening in this class. It's a perfect example. We're clumped. What else? Warmth in some places. Huh? Mating. Good. They got to have babies. So they need to be near each other in order for that to happen, right? And caring for young if they're K strategists. Obviously, populations can grow, shrink, they could stabilize, but there's going to be 4 main factors that determine growth, okay? So you're going to have growth, but you're going to have factors that determine that growth. What are they? Birth. What else? Good. And? Good job. Coming in or out, right, of an area. What would give me the formula for growth rate?
Number of births
Number of birth plus,
Immigration.
good, minus,
Death.
plus,
Immigration.
good job, equals growth rate. So those four factors determine growth rate, but if we're going to calculate natural growth within an area, we're going to only use what? Birth and death. And this is like a fun fact. You don't have to know this quote at the bottom, okay? But I wanted you to see what a difference it makes. Our population in 2 years in the United States from 2010 to 2012 grew by 5.17 million. 3.2 was natural. That means there was deaths and births being calculated. But 1.8 is due to migration. So that's a pretty big chunk. I mean, it's almost half of the, well, not half, but a big chunk came from that. So again, this is not any kind of number you need to know. What you will need to know is if I give you a birth rate, death rate, migration, or immigration, and I ask you, what is the growth rate? You know the formula. What is the natural increase? You know the formula. Yes? Okay. We normally don't calculate just how many births and how many deaths. We calculate how many births or death per 1,000 people in a population in a given year. And so this is another vocab word, crude birth rates, crude death rates. So number of death per 1,000 in a given year, number of birth per 1,000 in a given year. And then I can give you something like this, like a graph, and I could ask you, explain to me this graph. And who could give me anything that summarizes this whole graph? Love it. In the 1950s, birth rates seem to be significantly high, and now they're definitely, over the years, they've been dropping. And now you could see they definitely have almost half of what they had before, right? Well, not really 10. What else? Death rates. They're dropping also, not as high as birth rates. So you could say birth rates were really high in the 50s, right? Death rates were not so high, but they both declined. And I want you to add here, what happened in the 50s?
Baby boom.
Baby boom. Add that word in case you didn't know it. The baby boom occurred because?
At the end of the war.
End of the war, your soldiers came home. So you see the rule of 70 in a lot of things. It's a way to calculate or to determine a doubling time, or to determine, why is that happening? Annual growth rate. So the formula can be inverted, okay? So number of years it takes a population to double is equal to 70 over a growth rate. So some factor has to be given to you. The sad part is it's given to you and you can't use a calculator. Okay, so we're going to go over some problems, which here, obviously, you could use a calculator, but you won't be able to on the test. So doubling time is going to be T, and my annual growth rate is going to be R. So here's your first problem. If given 2010 world population growth rate of 1.3% per year, how long would it take the world's population to double, and by what year would this doubling occur? So we got T equals 70 over R. What are we given? The rate. So we're going to say T equals 70 over 1.30. And you're literally going to divide 70 divided by 1.30. You're not going to move decimals because here the T is per year, doubling time per year, and there's a per year. So something's canceling out, so you don't have to move the decimals. So what's the answer? Which is 54. And you use the calculator to do that, but you have to remember that you can't use a calculator, so you're going to have to do that math manually. I know, and it's not fun, right? When will the population double? What year? So this is your second math calculation.
2064.
Good. And I did a typo here, but obviously fix that. It's 2064.
Wait, what do you do? Yeah, I do that.
So you took 2010 plus 54 years is 2064. No, and calculate this. If the doubling time for the world's population is 56 years, what will the growth rate be? So what's given? T, which is what? So we got T equals 70 over R, right? 56 years. The answer is, we're not going to worry about the math, 1.25. So you're taking 70, right? You're inverting the formula. That's algebra. More reasons to calculate births and death is coming up. So fertility rate, number of children a woman will bear in her lifetime. And by this graph, you see where there's still some high fertility rates. But in this one, we calculate the total fertility rate, which is the average. And you're going to watch this change. So we started off with red usually everywhere. and we're getting to a lot of blue. And by the time we get to where we are today, fertility rates drop from 6 to 2. And honestly, how many of you have more than 2 brothers and sisters? More than 2. We're 4 people. If I asked that question 20 years ago when I started teaching, the entire class raised their hand, right? How many of your parents have more than 2 siblings? Look what happened. How about your grandparents? How many of your grandparents have more than 10? Yeah. Average number of children a woman will bear, or a couple will have in their lifetime is the replacement level. And obviously, by definition of species, you and your husband should have 2 children, right? Because that's your replacement level. But the replacement level fertility rates have dropped too. A lot of people are just having 1 child, which would affect, obviously, the growth rate a lot. All right, so no population can grow indefinitely, right? Because there's going to be factors that are going to limit population growth, and we call those factors environmental resistance. Something in the environment is going to stop the population from thriving. If there wasn't anything, that would be your biotic potential, where you can grow under ideal conditions, not realistically, right? There has to be resistance. Resistance can be determined by a lot of things. What would be something that would be resistance for us?
Wars.
Disease, war, water, food, right? Other organisms. So if you take the biotic potential and environmental resistance, you're going to be able to determine the carrying capacity, which by definition means what? Where have you seen this word? Good. And what?
In the thing yesterday.
You saw the carrying capacity? Oh, yeah, true. You did. But before yesterday, where do you see that word? Bio. In your life. An elevator. A restaurant. Yes? So, and that determines what?
How much can be before life starts?
Good. Maximum that can be supported, right, before something is going to happen. So if you look, when you measure populations, if you had no resistance, your population would thrive, right? But once you hit that carrying capacity, which is usually referenced by a dotted line, or if it's not referenced, you look at the population and you could see. If a population exceeds the carrying capacity, what do you think is going to happen? Death. And in this case, a population was getting near the carrying capacity and it stabilized before death, right? Because it was smart.